This video is going to cover the solutions to the tutorial problems associated with the sound topic. Okay, so this is problem 1. So this problem asks us to modify the pitch of a guitar string. You could change its mass, tension, or length. To raise its pitch, how should you change each of these characteristics? Okay, so if we're going to raise the pitch, what we want is the frequency to go up. So we've got a couple of equations that we'll need to use. We'll need to use V is equal to F lambda. And if we want this frequency to go up, then the frequency will go up if the velocity goes up, or if the velocity remains constant and the wavelength goes down. Okay, so let's start by considering the mass. How do we want to change the mass of the string? Well, the mass is going to affect the velocity because we've got our equation for waves traveling along a string that the velocity is equal to the square root of the tension over the mass per unit length. Now, we were saying if we want frequency to go up, it means that we want the velocity to go up. So we want this side to go up. If we want the velocity to go up, then we need this mass per unit length, mu here, we need that to go down. So if we want the mass per unit length, so mass per unit length needs to decrease. So mu is equal to the mass over the length. So if we want this to go down, then the mass needs to go down. So to have the pitch increase, we need the mass to decrease. So the mass of the string decreasing will increase the pitch. Okay, and then after the mass, it asks us to consider the tension. So again, we want the velocity to go up, as we've written in this equation here. And for the velocity to go up, the tension needs to go up. So the tension, sorry, I didn't spell that right, tension of the string increasing will increase the pitch. And then finally it asks us how should the length of the string change. Okay, so when we're listening to a musical instrument, it's mainly the resonant lengths that we pick up. So the first fundamental length, the string's vibrating like this, and the length of the string is equal to half a wavelength. But in general, the lengths that we will hear will be an integer number of half wavelengths. So in general, the length of the string will equal to some integer L times lambda over 2. Okay, so if we want the frequency to increase, then we've said that we want if the velocity remains constant, because it's the same string with the same tension mass per unit length, then we need our wavelength to decrease. And if we want our wavelength to decrease, then we also need this length of the string to decrease. So this will happen when the length of the string decreases. So to increase the pitch, we need the length of the string to decrease. So shorter length strings on instruments like harps, etc., tend to give the higher pitched notes. Okay, problem 2. So this problem says that the strings that play the lowest notes on a piano are made of thick steel wire wrapped with a spiral of heavy copper. The copper wire doesn't contribute to the tension of the string, so what's its purpose? Okay, so the lowest notes have a low frequency, so low frequency. And we know that V is equal to F lambda, and V is also equal to the square root of the tension over the mass per unit length. And so this tells us that the frequency is equal to 1 over the wavelength times the square root of the tension over the mass per unit length. Now, if we have a heavy wire, then it is going to mean that mu, the mass per unit length, is large. And if mu is large here, it's on the denominator in this fraction here. So that's going to give us small value here, so a lower frequency. So heavy wire means that mu is large and the frequency is low. So the function of the copper is to make the wire heavier, and by making it heavier, it reduces the frequency. So copper increases mass and hence mu, and hence decreases the frequency. Okay, problem 3. So in this problem, why we're replacing the air in an organ pipe with helium raise its pitch. Okay, so in this case, we've got sound waves traveling through air. And so the velocity of sound waves in air is given by the square root of B over rho, where this is the bulk modulus and this is the density. Now, helium is a very light, noble gas, and so helium has a lower density than air. Okay, so if rho is smaller, the density is smaller, so rho is smaller, then this means that the velocity, because we're dividing by a smaller number, so the velocity is going to be larger. And then we have V is equal to F lambda. If the velocity increases, it means that the frequency increases. So an increase in speed will mean an increase in frequency, is we're not changing the length of the organ pipe, and so the wavelength is going to remain the same, and so the frequency will need to increase to account for this increase in the velocity. So that's why we get a high pitch. And the same thing happens if you suck helium in. If you try to talk, then you have a funny high voice because of the lower density of the helium in your air tract. Okay, this is problem 4. So in this problem, tuning A for musicians has a frequency of 440 Hertz. And we're asked A, what's its period? So the period is the inverse of the frequency. So it's 1 divided by 440, and that gives us 2.27 times 10 to the minus 3 seconds, or we could write that as 2.27 milliseconds. Okay, part B then asks, what is the frequency of a note 3 octaves higher than 440 Hertz? So going up 1 octave doubles, that should be a no, doubles the frequency. So we have 440 times 2, there'll be 1 octave up, times 2 again, 2 octaves up, times 3. So that's 440 times 2 to the power of 3. So to go up 3 octaves, we have this power of 3 here. And then solving that, we end up with 3,520 Hertz is our new note. Okay, so problem 5. In this one, we're told that an orchestra plays with a tempo of 90 beats per minute, and each beat is divided into 8 short notes called demi-semiquavers. Okay, so let's start by working out the frequencies of these short notes. So we've got 90 beats per minute, and then we've got 8 of these notes in each beat. And then what we're trying to do is work out the frequency. So if we times this by 1/60, because there is 60 seconds in a minute, and then this is our frequency. Now, it's a good idea to carefully check all our units in this case. So let's put the numbers together to start with. So we've got 90 times 8 over 60. Now we've got beats in the numerator here and in the denominator there. So that beats is going to cancel out that beat. We've got a minute here in the denominator, and here we've got 1 on the bottom of the denominator. So if we have here 1 divided by seconds over minutes, we can write this as minutes over seconds. And so this minutes here will cancel that minutes there. And so our units for this quantity are notes per second. So that gives us the frequency of the notes. And if we work out what that is, it's 12 notes per second. So the period of a note is 1 divided by 12, because that's seconds per note. And if we want to do that on the calculator, it's 0.08333 seconds per note. Okay, and then it asks us if we have 2 musicians and it takes 1 demi-semi-quaver, which is this amount of time to get from one to the other, what distance are they apart? So distance is equal to speed times time. The speed, it's sound. So the speed depends on the temperature, but it's around about 340 meters per second times 0.830833. And solving that, we end up with around about 28 meters. We only want to give it to 2 significant figures because this 340 is only an approximation in the first place. So they could be 28 meters apart. And so it then says have a think about this result and what it implies for the size of orchestras. Well, I mean, you wouldn't want the orchestra to get much larger than this in length, because then when the musician was hearing the note that somebody else was playing on the other side of the orchestra, they'd actually be playing the next of these demi-semi-quavers. So there is actually a limit to the size of the orchestras because of this. Okay, so this is problem 6. So in this problem, we're told that guitar strings all have approximately the same tension T, and the photo shows a technique for measuring this tension, and it says, can you work out the details of how this works? Well, how it works is if we've got the strings here, we've got the tension in both halves of the string, and we've got the mass hanging down here. So this is a little force diagram of what's going on in this section. We've got the weight force pulling the string down, and then we've got the 2 tensions, and all of this is in equilibrium once it stops moving when the photo is taken. So if we let that angle in there be theta, what we know, if it's all in equilibrium, we'll be doing more on this in the mechanics course, is if we add all of these together, then they add to give 0. So we've got, this is one tension, this is the other tension, they're both the same, and we've got our weight force, mg, going down, and then that angle's theta, so this angle in here is 2 theta. So we know what the weight force is because we can measure that mass, and we know that g is 9.8. And we can also measure this angle here in the photograph. So if we know this angle and we know this length, then we can work out the size of the tensions because we know they're both the same. So that's how you can do it using this method. Okay, but onto the actual parts of the problem now. Part A says that the string that is lowest in pitch has a frequency of 82 Hertz. And we need to calculate the mass per unit length, mu. Okay, so in order to do this, we're going to need to use V is equal to F lambda, and it's also equal to the tension over the mass per unit length. So let's rearrange this because we're trying to find mu. So we'll rearrange it to make mu the subject. Okay, so let's start by squaring both sides. So we've got F squared lambda squared is equal to the tension over the mass per unit length. And then if we multiply this side by mu and this side by mu to remove it from the bottom and divide by F squared lambda squared, we end up with mu is equal to T over F squared lambda squared. Okay, so now we've got this equation. Now we know what T is. We were told in the question, I should have written it down up here. T is 50 newtons, so we know that one. The frequency we're told, so it's the wavelength that we need to worry about now. Now, in the question, we're told that the length of the string is equal to 645 millimeters. And the other thing we know is that this 82 Hertz, that's for the lowest possible sound. So for a string, the lowest possible note is going to be this fundamental, for which L is equal to half a wavelength. So the wavelength of this note is going to be 2 times the length. So that's going to be 2 times 645 millimeters. And so that is going to be equal to 1.290 meters. I've divided by 1,000 there to get rid of the millimeters. Okay, so now we have everything in this equation and we can just substitute in. So mu is equal to 50 divided by 82 squared times 1.290 squared. And we can solve this one and we end up with 4.5 times 10 to the minus 3 kilograms per meter. Or because it's kilograms per meter and we've got the minus 3 there, if we times it by 1,000, we'll end up with grams per meter. So that's 4.5 grams per meter, which sounds reasonable for a guitar string. We should always be asking ourselves when we've done a calculation if it sounds reasonable. If we ended up with 4.5 kilograms, for example, we'd know that something had gone wrong because a guitar string, 1 meter of it isn't going to weigh 4.5 kilograms. It's going to be fairly light. 4.5 grams seems reasonable. Okay, so part B then asks us the highest string is tuned 2 octaves higher. So it's tuned to a frequency of 82 times 2. That's 1 octave higher times 2. So 82 times 4, which is 328 Hertz. And we're then asked what's the value of mu for this string. So now we can substitute into this formula again. The strings have the same length on the guitar and we were told that the tension remains the same. So we've got that the tension here is 50 divided by the frequency squared, which is 328 squared, and times the wavelength squared, 1.290 squared. Solving this one on the calculator, we end up with 2.79 times 10 to the minus 4 kilograms per meter. And we should just give it to 2 significant figures because we only know the tension to 2 significant figures. So that's 0.28 grams per meter. We times it by 1,000 to get from kilograms to grams again. Okay, so now we've got the linear density of the 2 strings, and then part C says if the string has the same density, so that's rho, that is equal to the mass over the volume. This is what's the same, not the linear density. What would be the ratio of the thickness of the 2 strings? Okay, so we have the linear densities for the 2 strings. Let's put a little subscript 1 there and 2 there so that we're not getting confused between these 2 things. And what we know is that this density is the same. So the other thing that we can work out is that the linear density is equal to the cross-sectional area times the density. So the cross-sectional area are strings, are long cylinders, with, this is the cross-sectional area here, and it's got some radius there. So this is the area of a circle, which is pi r squared. And so just to show that this is true, let's just consider a unit analysis. This mu, that's in kilograms per meter. Area, the cross-sectional area here, that's in meters squared. And the density, that's mass divided by volume, so that's kilograms over meters cubed. And you can see meters squared divided by meters cubed gives us kilograms per meter. So this equation is true via unit analysis. Okay, so the linear density is equal to the cross-sectional area times the volume density of the string. And we know that the density is the same for everything. So density is also, as well as being mass over volume, rearranging this equation, is the linear density divided by the cross-sectional area. And this thing is not changing. So we have mu1 on A1 is equal to mu2 on A2. And this is what we're going to solve now, because we've got mu1 and mu2. Okay, so we can say mu1 on mu2 is equal to A1 on A2. A1 is just pi r1 squared. A2 is pi r2 squared, where r here stands for the radius of our circle, which is the thickness of the string in this case, or half the thickness of the string. Okay, so the pi's cancel out. Mu1, so that's 4.5 grams per meter over 0.28. So because this one here, we were multiplying by 4 here, which was going on the bottom. So it's effectively dividing by 16. So we'll end up with 16 is equal to r1 squared on r2 squared. So this tells us that r2 squared is equal to r1 squared over 16. And then taking the square root of both of these, we end up with r2 is equal to r1 on 4. So the second string with the lower linear density has a thickness which is 1/4 that of the string with a higher linear density. So the first string is 4 times the thickness of the second. Okay, this is problem 7. And in this problem, we're told that a band wants a didgeridoo to play the note C2, which is 65 hertz. So this frequency is 65 hertz. And the didgeridoo is to be made out of plastic pipe, which is cylindrical. And we're going to neglect end effects in this question. And we should consider it open at one end and closed at the other. And we want to know how long should it be. So this is the lowest note it needs to play. So this one here is our fundamental. And so for part A, we're playing the fundamental. So we've got, this is our wave inside the pipe. It's got some length L here, and we've got, that's 1/4 of a wavelength. So the wavelength is equal to 4L. And what we're trying to do is find L. And we also know that V is equal to F lambda. And because it's sound, V is around about 340 meters per second. So in this case, we have the 65 hertz. So we can rearrange this, and we've got that our wavelength is equal to V on F. That's 340 over 65. And so our wavelength is equal to 5.23 meters. And then the length, using this first equation up here, the length is equal to 1/4 of the wavelength. And so that's 5.23 over 4. And so that gives us 1.3 meters. And this time we've answered to 2 significant figures, as the frequency is given to 2 significant figures. Okay, now part B then goes on, if C2 is the lowest note played on this instrument, what would be the next highest note? Okay, so the next highest note, we're going to have this harmonic here. So we've got an open end here. So here we've got to have an antinode, and down here we've still got a node. So in this case, we've got 3/4 of a wavelength. So that the length is now equal to 3/4 of the wavelength. This is the third harmonic. And we know that the frequency of the third harmonic is 3 times the frequency of the fundamental. So the frequency is going to be 3 times 65, and we can solve that and end up with 195 hertz. If you didn't remember this relationship, then what you could do is work out the wavelength, because we know the length of the pipe here. So using L is equal to 3/4 of a wavelength, you can work out the wavelength and then use V equals F lambda and solve that to get the frequency, and you'll end up with the same result, 195 hertz. Okay, for part C, qualitatively, when the air in the instrument heats up or when it becomes humid, what do you think would happen to the density of the air? Okay, so when air heats up, it expands. So the density is going to decrease. Now, when air becomes more humid, we get more H2O in the air. H2O has a molar mass of around about 16 plus 2, so 18 atomic units. You're not expected to memorize that. This is a tutorial problem, not an exam type problem. Okay, and in air usually we tend to have N2 and a bit of O2. N2 has a mass of around about 28 atomic units, because nitrogen's 14 and then double it for N2, and O2 is around about 32 atomic units. So water is actually less heavy than N2 or O2. So when we say it's heavy on humid days, that's just a saying, it's not a physical reality. So the density decreases on humid days because we've got more of these lighter molecules in the air. Okay, and then it goes on, and what do you think would happen to the pitch? Okay, so if the density is decreasing, then we know that the speed of sound is equal to the bulk modulus divided by the density. So as the density decreases, we're dividing by a smaller number, and so our velocity is going to increase. And then we've got, the velocity is also equal to F lambda. This is not changing because the length of the pipe is not changing, so that's constant. And so if the velocity is going to increase, then the frequency is going to increase, which tells us that the pitch will increase. Okay, and that's how we do that problem. Okay, problem 8. Now, in this problem, we've got a string quartet with 2 violins, 1 viola and 1 cello. And then we're going to consider a chamber orchestra with 8 violins, 4 violas and 4 cellos. So in this case, we've the orchestra has 4 times as many players, and so that tells us that the intensity of orchestra will be 4 times the intensity of the string quartet. Or let's say I2, this is the orchestra because it's the second one mentioned, is 4 times the intensity of 1, the string quartet. And the question says, how much higher would you expect the sound level to be? Okay, so the sound level, beta, is given by 10 log to the base 10 I over I-O. Now, this question is going to be a bit tricky if you're not good at log rules, but yeah, this is how you do it. Okay, so the sound level for the string quartet, we're giving them a subscript 1, is equal to 10 log to the base 10 I1 over I-O. Remember, I-O is the reference intensity, the lowest intensity that people can typically hear. And beta 2 is equal to 10 log to the base 10 I2 on I-O. And I2 is equal to 4 I1. So we can write this as 10 log to the base 10 4 I1 over I-O. Now, the log rule that we're going to have to use is that if we take log of A, B, where this means A times B, this is equal to log of A plus log of B. So applying this rule to this line here, we can write this as 10 log to the base 10 of 4 plus log to the base 10 of I1 on I-O. And so we've got 10 log to the base 10 of 4 plus 10 log to the base 10 of I1 on I-O. Now I1 on I-O, 10 log to the base 10 of that is just equal to beta 1. So this is equal to 10 log to the base 10 of 4 plus beta 1. And so we can evaluate this. We can just put it into the calculator and we end up with 6.0 plus beta 1. So this tells us that the sound level, beta 2, is 6 more than the sound level for beta 1. So the answer to the question is 6.0 decibels. Okay, problem 9. So in this problem, we've got a sound wave which is described by the equation S of xt is equal to 6.6 times 10 to the minus 7 times cos of 2.1 x minus 730t. And that's in meters. And we're asked, and it travels through air with a density of 1.2 kilograms per meter cubed. And we're asked A, what's the maximum displacement of particles from equilibrium? So another way of saying this is what's the amplitude? So what's S max equal to? Well, S max is this number out the front. So in this case, the amplitude, the maximum displacement from equilibrium, is 6.6 times 10 to the minus 7 meters. And so that's the answer to A. Part B then asks what is the wavelength of the wave. Okay, so we know that K is equal to 2 pi on lambda, and that's the number in front of the X in this equation. So that's equal to 2.1, which tells us that the wavelength is equal to 2 pi over 2.1. And so solving this, we end up with 2.99, which is 3.0 meters to 2 significant figures. Part C then asks us what is the frequency of the wave. So we want to know the frequency, and we know omega is equal to 2 pi f, and omega is the thing in front of the t. So that's 730. So this tells us that f is equal to 730 over pi, 2 pi, sorry, and that when we solve it is equal to 116 hertz, which is equal to 120 hertz to 2 significant figures. And then it asks you to try and imagine how this sounds. So maybe just try playing that note on one of the free frequency generators. It's fairly low. And now D asks us what is the speed of the wave. So we want to work out V. We know V equals F lambda. Probably with the information we've got here, we could just substitute in F and lambda if we wanted, but it may be simpler in this case to write this as 2 pi F times lambda over 2 pi. So that's omega on K. Omega is equal to 730. K is 2.1. And solving this, we end up with 348 meters per second, which is 350 meters per second to 2 significant figures. Part E then says, what is the maximum change in pressure as the sound wave passes? Okay, so we know that delta P max is equal to rho V omega S max. So that's one of the equations that we were kind of showed and presented with in the lectures. Okay, so all we need to do is substitute in here. We know what omega is. We've worked out V. We've worked out omega. S max we've worked out. So we're just literally substituting in. So 1.2 times 348. For the working, we keep the extra significant figures. Omega, that is equal to 730. And S max, that's 6.6 times 10 to the minus 7. Solving that one on the calculator, we end up with 0.20 pascals as the maximum pressure change as the sound wave passes. Part F now asks us if this wave simultaneously passes through all points on the sphere 1 meter from the source of the wave, what's the average power? Okay, so our formula for average power, which we're going to need to substitute in for, is 1/2 rho v omega squared a S max squared. Now, most of these terms are very straightforward, and we've evaluated them above. The only slightly complicated one is A. A, remember, stands for the area, the surface area in this case, not the amplitude. S max is the amplitude. So in this case, it's passing through a sphere. So that's got a surface area of 4 pi r squared. So that's equal to 4 pi in this case because the radius is 1. Okay, so just substituting in, we've got 1/2 times 1.2 times 348 times 730 squared times 4 pi times 6.6 times 10 to the minus 7 squared. And we can solve that on the calculator, and we end up with 6.0 times 10 to the minus 4 watts. And then finally, part G says write the equation to describe the same wave when it's 3 meters from the source. Okay, so if we have the same source, the average power is going to be the same. The density of the air does not change. The speed of the sound does not change. The frequency of the wave does not change. The area over which the wave is spread does change. It becomes 4 pi r squared, which is 4 pi times 9 in this case. So the area is 9 times bigger. So area is 9 times larger. And to compensate for that, the amplitude of the wave actually decreases. So S max squared is going to be 9 times smaller. Now, if S max squared is 9 times smaller, it means S max is the square root of 9, which is equal to 3 times smaller. So that tells us that the S max is equal to 1/3 of the old S max, which was the 6.6 times 10 to the minus 7 meters, which is 2.2 times 10 to the minus 7 meters. So we've now got a new amplitude, but everything else about the wave has remained the same. So we will now have S of xt is equal to 2.2, that's an equals 2.2 times 10 to the minus 7 times cos of 2.1x minus 730t. Okay, and that's in meters. So that's the equation for the wave when it's progressed on. So as waves move further from the source, the amplitude decreases, which is why they sound fainter to us. This is problem 10. For this problem, we're given two waves. We've got y1 of xt is equal to 0.300 sine 1.23x minus 450t meters, and y2 is equal to 0.300 sine of 1.23x plus 450t meters. And in the first part, we're asked to describe physically what these waves would look like and what are their similarities and differences. Okay, so these are both traveling waves, both traveling waves with an amplitude of 0.300 meters. We can also work out the wavelength and the frequency. The wave number is equal to 2 pi over the wavelength, and that's equal to 1.23 meters. And so that tells us that the wavelength is equal to 2 pi over 1.23, which is equal to 5.11 meters, and the omega is equal to 2 pi f, which is equal to 450, which tells us that the frequency is equal to 450 over 2 pi, which is equal to 71.6 hertz. And we could even work out the speed. The speed, we can use omega on k, which is equal to 450 over 1.23, which is equal to 366 meters per second. Now, how these waves are different is because this one's got a negative here and this one's got a positive. This first wave, y1, is moving in the positive direction. The numbers in front of this term and this term have opposite signs, so it's moving to the right. So y1 is traveling to the right, and y2 is traveling to the left. Okay, now in part B of the question, it asks us write down an equation for the superposition of the two waves. So to get the superposition, we have to add y1 plus y2. So we can write this as equal to, we'll take the amplitude out the front as a common factor. So it's sine 1.23x minus 450t plus sine 1.23x plus 450t. Now, you might remember a quick way to do this, which is fine, but if you don't, then you'll need to work through using the relationship sine A plus sine B is equal to 2 sine A plus B on 2 cos A plus B on 2. And in this case, this thing here is going to be our A, and this thing here is going to be our B. So we've got sine of A, which is this thing, plus sine of B, which is that thing. Okay, so using this rule with this, we've got y1 plus y2 is equal to 2 times 0.300. And now we've got sine of A plus B. So this plus this. When we add this plus this, the minus 450t will cancel out with the 450t. So we'll have 2 times 1.23x over 2, and then times cos of, sorry, that's a typo, that should be A minus B. So now we're doing this minus this. When we subtract this from this, the 1.23x's cancel out, and we end up with 2 times minus 450t on 2. Okay, so these factors of 2 cancel out, and we have 2 times 0.300, so that's 0.600, sine 1.23x cos of minus 450t meters. And we could leave it that way if we want, or we could use another trig rule that cos of x is equal to cos of minus x. So we can replace this minus 450 with 450. Okay, so that's the equation, and we're then asked in part C to describe physically what this wave looks like and what's the name for this type of wave. Okay, so this is called a standing wave. And it's called a standing wave because we've split it into a spatial component here and a temporal component here. So the pieces of string move up and down in simple harmonic motion with amplitude, with, well, a maximum amplitude of 0.600 meters. And we could maybe sketch what it's going to look like. Each piece is going to oscillate up and down like that, and we can say, well, the amplitude is 0.600 in the middle here. It goes down to 0 there, and the wavelength for the standing wave is still going to be 5.11 meters, and the frequency of these oscillations up and down is still going to be equal to 71.6 hertz. This is problem 11. So in this problem, we've got a tuning fork with an unknown frequency that makes a beat frequency with another tuning fork of 384 hertz. Okay, so let's call this one FU. U stands for unknown. So this tuning fork has some unknown frequency, and then there's another tuning fork here with a frequency of 384 hertz. And we know that F beat is equal to F minus F underscore U. And so this F beat equals F minus FU, or F beat equals FU minus F, depending on which one is larger. Okay, so in the question we're told that F beat is equal to 3, and the other thing that we're told is that the beat frequency decreases when plasticine's added. So when we add plasticine to something, it makes this bit heavier, and so that'll make FU decrease. So if FU decreases, then the beat frequency decreases. We can see in this one, if FU gets smaller, then we're subtracting a smaller number, and so the beat frequency is actually going to increase. In this case, where FU is bigger than the frequency F here, then if F beat gets smaller, if this gets smaller, then F beat is also going to get smaller. And so that tells us that this one must be the equation that we're going to have to use. So we have 3 is equal to FU minus 384, which tells us that the unknown, F unknown, is equal to 3 plus 384, which is equal to 387 hertz. So this one's problem 12. This problem's quite difficult. In this one, we've got a piece of wire with a mass hanging off it. This is a 10 kilogram mass, and so it's applying a downwards weight force equal to mg, which is equal to 10 times 9.8, which is equal to 98 newtons. And this piece of wire is made up of 2 parts. We've got a length 1 there, which is aluminium, and then a length 2 here, which is made up of steel. And we're told in the question that L1 is equal to 60 centimeters, so that's 0.600 meters, and L2 is equal to 86.6 centimeters, so that's equal to 0.866 meters. And we're told that the cross-sectional area of this wire, so the wire's got some, say, circular cross-sectional area here, A, and A is equal to 1.0 times 10 to the minus 2 centimeters squared. Okay, now let's start by converting this into meters squared, because if we have everything in SI units, it'll save us getting confused later. Now, in 1 meter is equal to 100 centimeters. So in 1 meter squared, there's 100 squared centimeters squared. So to get from centimeters squared to meters squared, we have to divide by 100 squared. So this is 1.00 times 10 to the minus 2 centimeters squared times 10 to the minus 4, that's meters squared per centimeter squared. And so this is equal to 1.00 times 10 to the minus 6 meters squared. Okay, now we're going to set up standing waves in this wire here. And we know that there needs to be a node between the two wires. So for that to be the case, we know that in length L1, there has to be some integer. So we'll use n to represent an integer, n1, number of half wavelengths. Okay, so times lambda 1 on 2. We also need to have standing waves in this second wire, as we know we've got a node there and we have to have a node at the pulley. So in wire 2, there's some other integer number of half wavelengths. Now, because this is waves in a string, we know that V is equal to F lambda, and it's also equal to the square root of T on mu. And we know what T is here. The tension's caused by this hanging mass, so it's the 98 newtons. And we can work out what mu is. Mu is equal to the mass per unit length, so it's equal to the cross-sectional area times the density. So it'll be different for the two wires because we've got different densities. We're told that in aluminium, the density is equal to 2.60 grams per centimeter cubed. And in steel, we've got the density is equal to 7.80 grams per centimeter cubed. Okay, now we want to put this into SI units. So this is 2.60 grams over centimeters cubed. First of all, let's convert from the grams to the kilograms. So in 1 kilogram, we have 10 to the minus 3 grams, 1 divided by 1,000. And the other thing we want to do is convert from centimeters cubed to meters cubed. In 1 meter, there's 100 centimeters. So in centimeters cubed, we need to do the 100 to the power of 3 centimeters cubed per meter cubed. So this thing is equal to 10 to the 6. Okay, so what we end up with is 2.60 times 10 to the minus 3 times 10 to the 6, so that's 10 to the 3. And then looking at our units, these cancel out and we've got kilograms per meter cubed. And then what we can do is work out our linear density, mu1, which is A, the cross-sectional area, which is 1 times 10 to the minus 6, times 2.60 times 10 to the 3. And so this gives us 2.60 times 10 to the minus 3 kilograms per meter. And similarly, we can work through with the density of the steel, which is here, and we end up with mu2 is equal to 7.80 times 10 to the minus 3 kilograms per meter. Okay, so now we've got the linear densities and we've got the tension for the two wires. We've got one frequency generator, so we know that the frequency in the two wires has to be the same. So let's rearrange this formula, and we've got that the frequency is equal to 1 over the wavelength times the square root of the tension over the mass per unit length. And so we can say, well, 1 over lambda 1 times the square root of T over mu 1 is equal to 1 over lambda 2 times the square root of T over mu 2. And now we've got expressions for lambda 1 and lambda 2 here. So this one we can rearrange as lambda 1 is equal to 2L1 on N1, and similarly here. So instead of 1 on lambda 1, we can put N1 over 2L1 times the square root of T over mu 1 is equal to N2 over 2L2 times the square root of t over mu 2. And now we can cancel out the common factors. So the tension's the same, and this 2's the same. And so we can now get an expression, N1 on N2, just rearranging this, is equal to L1 on L2 times the square root of mu1 on mu2. And so now we can work out what N1 on N2 is, because we've got expressions for this. So we've got 0.600 over 0.866 times the square root of mu1, which is 2.60 times 10 to the minus 3 over 7.80 times 10 to the minus 3. And then we can solve this on the calculator, and we end up with 0.400. So N1 and N2 are integers, and this is equal to 4 over 10, which for the smallest integers that satisfy that are 2 over 5. So this tells us that N1 is equal to 2 and N2 is equal to 5. And physically, what that means is that we have two half wavelengths in this one. So we've got one wavelength there, and then in this second one, we've got 5 half wavelengths. So the actual string's going to look a bit like that. Now, what we've been asked to find is the frequency. So just looking at this, we know that the frequency is equal to the velocity over the wavelength. The velocity is equal to the square root of t on mu times 1 over wavelength. And then just considering this first part, L1 here, we've got the square root of the tension's 98. The mass per unit length was 2.6 times 10 to the minus 3. And the wavelength, that's equal to L1, the length of the string, because we've got two half wavelengths on that length of string. So that's times 1 over 0.600. And then we can solve that one on the calculator, and we end up with 324 hertz as the frequency there. Now, part B then asks us, what is the total number of displacement nodes observed at this frequency, excluding the two ends of the wire? Okay, so we can now use the little diagram that we've drawn up here. We don't count this node, we count this one. So we've got 1, 2, 3, 4, 5, 6. So we've counted 6 nodes. So the answer to this one is the 6 nodes. So that last part wasn't too hard once we'd done all the work to get the first part out.